All right, so let's look at example 2 now. So for f of x equaling x cubed minus 3x squared minus 5, let's find everything and then sketch the graph. So the first thing we want to find is our domain. And it's important to note on the test, I will give you all the steps laid out like this. So you won't need to go back and know what order to do the steps in and everything. I will give you the steps. You just need to be able to actually do every single step. All right, so for the domain, in this case, we know that f of x is a polynomial. So our domain is negative infinity to infinity. The critical numbers, so we want to find the derivative and set it equal to 0. We know in this case our derivative is going to be a polynomial since f of x is a polynomial. So that means that f prime is never going to be undefined. And so f prime of x, in this case, so derivative of x cubed is 3x squared minus the derivative of 3x squared, which is 6x, minus the derivative of 5, which is 0. And so then setting this equal to 0, 0 is equal to 3x times x minus 2. So then 3x equals 0 gives us x equals 0. X minus 2 equals 0 gives us x equals 2. So our only two critical numbers in this case are x equaling 0, x equaling 2. Now let's find the open intervals where f is increasing or decreasing. So looking at our intervals, our domain is our starting point, negative infinity to infinity. And we want to split it up when x equals 0 and x equals 2. So somewhere on negative infinity to 0, let's pick the value x equals negative 1. So then f prime of negative 1 is going to equal to 3 times negative 1 times negative 1 minus 2. So 3 is positive, negative 1 is negative. Negative 1 minus some stuff, minus negative 2 in this case, is also going to be negative. So we have positive times negative, which is negative, and then negative times positive, which is going to make that positive. So this is greater than 0. So f is increasing there. On the interval 0 to 2, let's pick x equaling 1. So f prime of 1 is 3 times 1 times 1 minus 2. Again, make sure you're showing me all this work. Otherwise, you're going to lose points on the test. So then 3 is positive. 1 is positive. 1 minus 2 is going to be negative. So we have positive times positive. A positive times a positive is positive. So we have positive times a negative. So that's going to be negative less than 0. So f is decreasing on that interval. And then from the interval 0 to 2, then let's pick 3. X equals 3. So f prime of 3 is 3 times 1 minus 3. So 3 is positive. 3 is positive. 1 minus 3. Oh, sorry. 3 minus 2. That's what I get for looking at my line above. 3 minus 2 is positive. So we have positive times positive times positive. So this is greater than 0. So f is increasing. So it's going from decreasing to increasing to decreasing. So f is increasing on the open intervals negative infinity to 0. Sorry, I don't know why I drew a decreasing there. It's going increasing decreasing, increasing. So f is increasing on negative infinity to 0, union 2 to infinity. And f is decreasing on 0 to 2. All right, for part D, the open intervals where f is concave up, concave down. So we need our second derivative. So f double prime of x is going to be 6x minus 6. Which then is 6 times x minus 1. So now we want to set this equal to 0. So that gives us x minus 1 equals 0, so x equals 1. Could be a point of inflection. So same idea. Now we start with our domain, negative infinity to infinity. Split it up at our possible point of inflection of 1. So somewhere on negative infinity to 1, let's choose x equals 0, because that's a nice easy number to substitute. It also happens to be one of our critical numbers, right? So then we're killing two birds with one stone. We're doing the second derivative test at the same time that we're checking concavity. So x equaling 0 means f double prime of 0 is 6 times 0 minus 1. So 6 is positive. 0 minus 1 is negative. So we have positive times negative. So that's less than 0. So f is concave down. And then for 1 to infinity, why not pick our other critical number 2? Again, killing two birds with one stone here. So x equaling 2. So f double prime of 2. 6 times 2 minus 1. So 6 is positive. 2 minus 1 is going to be positive. So we have positive times positive greater than 0. So f is concave up there. So we know then our intervals of concavity. So f is concave up, down. On our first interval, negative infinity to 1. And then concave up on 1 to infinity. So now, relative extrema, well, we just checked our two critical values with the second derivative test, right? We also have the work from the first derivative test on part C if we wanted to use that. I like the second derivative test, so I'm going to use my results from here. So f double prime of our first critical number, 0, was less than 0. So if remember, if the second derivative at the critical number is less than 0, then we have a relative maximum. At 0 and f of 0, so we need f of 0, so that's 0 cubed minus 3 times 0 squared minus 5, so f of 0 is negative 5, so we have a relative max at 0, negative 5, and then x equaling 2 is going to have, well, so the second derivative at 2 was greater than 0, so that means by the second derivative test we have a relative minimum at 2f of 2, so same thing, find f of 2, so that's 2 to the third power minus 3 times 2 to the second power minus 5. You work all that out and you end up getting negative 9. So we have relative max at 0, negative 5, relative min at 2, negative 9. Part F, point of inflection. So we're looking for the concavity to change, and it does. It went from concave down to concave up at x equaling 1. So we have a point of inflection because it's in our domain, right? It's at 1, f of 1. So f of 1 is 1 to the third power minus 3 times 1 to the second power minus 5. And that equals negative 7. So we have a point of inflection at 1, negative 7. Our y-intercept we've already found, so that's whenever x equals 0, so 0, negative 5. We've already done the work to get f of 0. And so now we're going to put all of this together to sketch our graph of f of x equals x cubed minus 3x squared minus 5. So there's my x-axis, my y-axis. Let's label We know we're going to need down to at least -9. I'm just going to go down a little bit further. So -1, -2, on down. And then the x-axis label some values on both sides. All right, so let's plot everything we know. So I always start out with the points I know. So I know I have a relative maximum at 0, -5. So there's my relative maximum. I have a relative minimum at 2, -9. Since this function's not rational, we don't have to worry about asymptotes. I have a point of inflection at 1, -7. So there's my point of inflection. So now we know f is going to be increasing on -infinity to 0. And then it's also concave down on -infinity to +1. So concave down with what we know is a relative maximum here has to look something along the lines of this. So there's our part where it's increasing and concave down, and then we go to decreasing concave down from 0 to 1. We're still decreasing from 1 to 2, but then we're concave up. So now we've got concave up with the relative minimum, and so it's going to look like that. And so notice how this looks like our cubic function.